Hello?
Hi, how are you
Hi.
doing?
Are you Amy?
I'm good, thanks. How are you?
Good. Sorry, are you Amy?
Yes, I am. Yeah,
Okay. Nice to meet you.
you too. Yeah, so I mean, I guess we can just hang around until people start to join. Yeah.
Okay. I will try to share my screen and check that everything works.
Yeah, that would be great. Thank you.
I need to be a host to share my screen.
Ah, yes. Okay, that should be working now.
Okay. Yes. Okay, can you see my screen?
Yes. Yeah, I can. It looks great.
Full presentation mode and
Yeah,
okay, perfect.
perfect. How is your, well, I mean, I guess it's been a long lockdown or long stretch of COVID, but how's it going there?
Still bad. Ontario is a disaster. Yeah. I don't know what happened, but after the second wave, we have the third one. We are now in the third one. And it was much higher than the second one. I don't know why exactly. And now we are going in the right direction, but still we are in a stay-at-home order, which means that everything is closed except grocery stores and pharmacies. That's it. And we cannot meet with anyone that is not in our household and this kind of stuff. So yeah, going in the good direction and the vaccinations are improving, but still, yeah, we are kind of trapped.
Is that in, because you're at University of Toronto now, right?
Yes.
Right.
This Ontario, it's all the province. So yeah.
Okay.
And of course, a city as Toronto is much worse than other regions because there are more people.
Yeah, I've heard a lot about the States, kind of their COVID response, but I haven't really heard much about Canada. So this is the first.
Canada was doing great until this third wave. It was a complete disaster. So, and how about you? I mean, the UK is much better now, right?
Now, yeah, I mean, now it's getting better, but I think sort of over December, January, we had a really long lockdown, and that was quite tough. But yeah, now it's sort of
everybody in Europe was. I just escaped from Spain just when everything started, so March 15 or so. Okay. I was flying the day that it was declared like the emergency state or something like that. So when all countries in Europe just closed, so it was a crazy days.
I can imagine. Yeah. Wait, emergency state in Europe or in Canada?
In Europe, and then I went to Canada, and Canada was kind of okay. And then the lockdown arrived to Canada, and so it's just quarantine after quarantine, just in case.
That was good timing then, because I grew up in South Africa, and I flew back just as like the South African lockdown ended and the British one kind of was still going on. So I kind of moved like with the lockdowns, which was quite bad, but now it's fine. So yeah.
And by the way, you're in Oxford now, right?
Yes, I am. Yes.
And where are you located? Because I was in Oxford for months during my PhD, but I was in physics faculty. I was not working in quantum information. I was working in particle physics.
Right.
So it's just curious, where are you located in?
So my college is St. Hugh's, but my department is physics, atomic and laser physics. So I'm co-supervised by Vlatko Vedrol and Sam Abramsky, who's in computer science. So it's quite nice because I've like got some kind of split between the two. But yeah, I did work a bit on VQE in summer because I was working at Cambridge Quantum Computing.
Okay.
So I'm looking forward to your talk. I mean, probably won't be able to understand all of it, but I think it should be interesting. So I saw you were working on sort of more foundational stuff in your thesis, and now you're kind of like you've moved over. In
the end, the thesis, I just move around many topics, and then I ended up in quantum computing because I started working in Barcelona Supercomputing Center, and they founded a group in quantum computing. So that's why I just focus on that. And it was at the same time. So I remember I was in Oxford when IBM launched the first open quantum computers in the cloud. So I remember I was there and I was just texting my supervisor back in Barcelona and saying, oh my God, do you know that there is now a quantum computer that we can use on the cloud? And it was only the 5-qubit one. Yeah. And it's crazy how many things have changed in all this time. So I remember that day, and I think it was, the beginning of working more towards quantum computing instead of other fundamental things in quantum information. Right. Although now I'm kind of reconnecting with it, because now I'm working in high dimensional quantum information, like Q-trees instead of qubits and this kind of things. So it's kind of coming back to the past somehow, but also running everything in real quantum computers. So you still need to do computation somehow.
Yeah, I find that really exciting, being able to actually just use quantum computers on the cloud. I think it's, the fact that it's all open source and stuff as well is great.
Yeah, that's good, especially for theoreticians like me. That, I mean, it's the only opportunity probably that you will have to run a real experiment, or the closest thing to a real experiment that you can do. So it's great. Yeah. Okay, so you're a PhD student. You're starting now.
Yes, I just started. So I did my undergraduate at Manchester, and then I did a year abroad in the States, which got me really into like quantum information. And I was sort of set on doing the more applied side, and then I came back and sort of got more into the foundational side. So I've just started now, but it's a really exciting field, I think, and also sort of it's nice that there's the option to have like the industry there.
Indeed, yes.
Okay, I will quickly start recording or start sharing live on Facebook. Right.
Also, could you tell me what will be the format? So, for instance, people will ask questions in the chat, or
so okay, so we're live now, so that's good. After the talk, there's a Q&A, and then I'll just read out the questions, and and you can answer them, and then I think the talk format is around between 45 and 60 minutes, but I mean, just however long you want, really. There's not we're not very strict on that. So just before you start, I'll read out some stuff. Wait, let's wait until 5 past just to let a few more people join.
No problem.
So did you do your undergraduate? You did your undergrad and PhD, right, in Barcelona?
Yeah, everything in Barcelona, also my master's. And my experience outside Barcelona was precisely going to Oxford. So I miss Oxford very much. So I really enjoyed my time there. It's super nice city. And then I came here to Toronto almost 2 years ago. So it's not the postdoc that I was expecting, as you can imagine, as everybody can imagine, because I've been in lockdown 1.5 years, over 2 years of postdoc. So, but anyway, no, not 1.5 years, but now more than 1 year, yes. So
at least you have something to look forward to. You can see Toronto when it's like fully open.
But right before COVID, I had the opportunity to travel around Toronto. So I mean, not Toronto, but going to some region in Ontario. So at least I visit slightly something beyond Toronto, but
no, that's lovely. I've never been, but I've heard great things about Canada, specifically in terms of quantum information, obviously. So I think you're super lucky to be there.
It's a great environment. You have Vector Institute, you have also University of Toronto and Creative Destruction Lab as a startup incubator. So, and not only in Toronto, also in Sherbrooke, you also have some groups in quantum information and quantum computing. So, and Waterloo, of course, which is very close by, like 1 hour or so. with the IQC Center. So it's a great area for quantum information, I would say.
Yeah, and the Perimeter Institute.
And Perimeter, of course, yes, yes.
All right, okay, let's get started then. So I'll just read out a short introduction. It's also very windy here, so apologies for the noise. Okay, so hi everyone. Thanks for joining us today for another talk in Oxford Quantum Information Society's talk series, where we have a number of speakers, both from within foundations and applications of quantum information. Earlier this week, we had Professor Carlo Rovelli, who spoke about relational quantum mechanics. So today we have Alba Cervera-Lierta. So Alba received a PhD in 2019 under Jose Ignacio Latour, in which she studied maximal entanglement in quantum information and particle physics. Alba is currently a postdoc in the Cervera-Lierta lab at the University of Toronto, where she is working on quantum algorithms. In particular, today she will be presenting some work in which the standard variational quantum algorithm, or VQA for short, approach is adapted so as to account for some issues in the original framework, such as Var and Plateaus. Okay, so without further ado, I'll hand over to Alba.
Thank you very much, Amy, for this kind of introduction. Let me share my screen. Okay. So hello, everyone. Thanks for the invitation. It's a pleasure to talk here. I would like to visit Oxford in person, but unfortunately that's not possible now. I miss that city very much. I was there during my PhD as well. But anyway, it's nice to have the opportunity to present my work and also the work of some of my collaborators, because I will present 3 topics here. One is, of course, the Meta-Variational quantum Eigensolver. I will finish my talk with that, but I will start first presenting Tequila, which is a platform that we designed to develop quantum algorithms. So it's a quantum package language that I will explain briefly how it works, because it's open source, it's open for everyone, and we encourage contributions for anyone that wants to add some new features to this platform. And then I will review what is a variational quantum algorithm. And for that, I will rely on a review that we published recently, a few months ago. And then I will make some break to talk about quantum machine learning in the context of variational quantum algorithms, because that's what we will use to design the Meta-Variational quantum Eigensolver. So, and finally, we'll close with this algorithm. So let me start with Tequila, which is this, as I said, this package for quantum computing. And the idea of Tequila, the motivation comes from the fact that now we are kind of in a golden era of quantum languages. As you may know, there are many quantum languages. And for that, I mean software packages, because a quantum computer, the hardware is quantum, but the software is classical. We have to control the computer, the hardware from the outside with some set of instructions in the end. So that's why basically every company and every research group, or almost every research group, has their own language, have developed their own package, of course, to control the machines that they are building, or to build clever simulators that can go beyond 20, 30 qubits as much as possible. And that's why there are so many quantum languages, and some examples are Qiskit, which is developed by IBM, Cirq, which is developed by Google, PyQuil, developed by Rigetti. We also have Kibo, Penny from Xanadu, Q-Sharp from Microsoft. We have many of them. Also in Cambridge Quantum Computing is Ticket, so there are many. But besides these quantum languages, we also have quantum software packages and tools that help us to control these languages. So for instance, we also have Psi4 and OpenFermion, which are 2 libraries for quantum chemistry. And these libraries will be very useful, especially for these variational quantum algorithms. So we need a way to fit together these quantum languages, which is to design our quantum computer, our quantum algorithm, and on the other side, using the available classical tools that we already have. Also, all the packages that help us with optimization, etc., that will be very useful. So that's why we also need these classical tools for the NISQ era, where NISQ stands for Noisy Intermediate Scale Quantum, which is the current era in quantum computation. So as you may know, we have quantum computers, but they are small. They are devices with a few qubits. And these qubits are noisy, which means that they cannot perform perfect algorithms like Shor factorization algorithm or Grover search. And that's why we have to come out with other strategies to take advantage of these devices at short term. And for that, we created the variational quantum algorithms and also other kinds of algorithms. And that's why we need to put together the best tools from quantum and also classical to squeeze these current quantum computers. So in the end, we have many. And the problem from our point of view as a researchers, as a theoretical researchers, some of us, is which language should I pick? Because there are many of them, all of them are great. Some of them have some features that are better than in others. And what happens if I want to benchmark my algorithm, if I want to compare them? So if I wrote a code in Qiskit and then I want to run it in another quantum computer, then I need to translate my code to another quantum computer, which means I basically lose my time doing my job twice or three times or more just to benchmark my algorithm. So that's why we were thinking about how can we implement our algorithms in any platform so we don't have to learn every time a new language. And that's why we developed Tequila, which is a platform that aims to only program in one language and unify language. And then by just changing one line of code, which is specifying your backend, you can just change from Qiskit to Circ, and you don't have to care about how is the current language. Everything is done under the hood. And on top of that, we also want to aim to put together different features, for instance, the quantum chemistry ones that I mentioned, and also other libraries that are being developed for different applications in quantum computing. And we are working on that. So the Tequila platform is already on. You can use it. We are using it all the time. For instance, for this Meta-Variational quantum Eigensolver, everything is programmed in Tequila. And the idea is that we just want to construct a growing community that uses it and also introduces new features. So this is developed from academics, from academia and beyond. So please take a look on the code repository and also the tutorials that we are creating, and let us know if there are issues or if you want to contribute. We will be more than happy. Let me explain briefly how the Tekilapi works, so I can give you an example. So we normally, with all these algorithms, we start with some operator, some Hamiltonian that we want to extract some information from it, for instance, the ground state energy. And for that, we construct a quantum circuit that will compute this expectation value. So to design this quantum circuit, that's the first step in quantum computing, how we construct this quantum circuit in the first place, which gate should we use, etc. And there are some techniques, especially in quantum chemistry, that tells you how to design this quantum circuit depending on the Hamiltonian that you have. For instance, the unitary coupled cluster ansatz is one of the most used ansatz in quantum chemistry in the context of quantum computing. But also to create this Hamiltonian, if you are not a chemist, or even if you are a chemist, you need to find a way to map your molecule to the electronic structure Hamiltonian that represents the molecule, and to select the orbitals that you want, the approximation that you want, etc. And for that, there are some well-known packages, for instance, OpenFermion and Psi4, that do that for you. So what we do in Tequila is mix these packages with Tekilapi. So you only call one line of code just to say, yeah, I want this molecule with these orbitals in this representation and these basis elements. And it constructs automatically the Hamiltonian and decomposes it into Pauli strings, which is the things that we will eventually measure in our quantum computer. So once we have Hamiltonian on our quantum circuit, we can compute the expectation value. But this expectation value is translated into what we call objective function. The objective function is something more sophisticated than an expectation value because it could be any function of this expectation value. So it's not necessarily just one expectation value. It could be some combination of them. You can construct more than one, and that's what we will use later on in Meta-VQE. And then once we have these objective functions, we send it to the backend. And this backend could be a real device or could be a simulator, for instance, QLAGS or the Qiskit simulator. And in this process of sending everything to the backend, we can also introduce noise models, sampling, or just simulating the exact wave function if the backends allow that. So it depends. As more backends we have installed in our computer, the more things that we can try. And then we also can mix this backend with the classical optimizer that will be useful in variational quantum algorithms, as I will explain later. And for that, we also need to mix everything with all the optimization methods, for instance, the ones that are in SciPy. So this is also implemented in Tequila. So you just have to select which optimization method do you want to use, how do you want to compute the gradients of the function, etc. And besides all of it, we also have other features, for instance, drawing the circuits, defining the gates manually. So instead of defining a well-known gate like control node, you can also design the gate by constructing the Hermitian operator and designing the gate in this way. And we are also implementing other features, for instance, circuit compilation using the ZX calculi and using other libraries that already exist. So the idea of Tequila is to put everything together, and so you don't have to worry about how other packages work and only focus on programming your quantum algorithm. Okay, let me move to the next part of my talk, which is what are these variational quantum algorithms that I've been mentioning. And for that, I will rely on this review that we published a few months ago on noise intermediate scale quantum algorithms. And I just want to stress out that variational quantum algorithms are some kind of this noise intermediate scale, but not the only ones. So there are other approaches that are also interesting in that direction. So what is a variational quantum algorithm? Some well-known examples, maybe you heard about them, is the variational quantum Eigensolver or the quantum approximate optimization algorithm, or QAOA for short. And the idea is actually, all of them rely on the same idea, which is mixing the capabilities of a quantum computer with the capabilities of a classical computer in the following way. So we start with some initial state that could be just the 000 state, which is the state that the quantum computer is initialized, or could be any state that we know how to construct, and maybe it's the first approximation of our solution. For instance, in chemistry, people normally use the Hartree-Fock approximation, which in the end can be decomposed into a product state, so it's easy to construct for us. Then we introduce this initial state, we initialize our quantum circuit with it, and we've pass through a quantum circuit that depend on a series of parameters. So this quantum circuit, we need to design it, and that will be one of the problems in these variational quantum algorithms, how we design this quantum circuit. But the key idea is it depends on some parameters. For instance, we can have rotational gates where the angle of this rotational gate is one of these parameters. So once this circuit evolves, we have some output, and with this output, we compute the expectation value of our objective function. For instance, our Hamiltonian, as I said before. So once we have this expectation value, we want to minimize it because we have the variational principle. We know that whatever value that we obtain will be an upper bound of our ground state energy. So we want to minimize this upper bound precisely and finding what is the ground state energy in this particular example. So for minimization, we introduce this parameter and the gradients of this expectation value into a classical minimizer. So for instance, a gradient-based minimizer, a stochastic gradient descent, or any other method that you can think about. And this minimizer would suggest a new set of parameters of our quantum circuit. So in the end, we are trying to fine-tune the parameters of the quantum circuit in order to minimize this expectation value. So eventually, after repeating the process many times, we will converge to some solution, to some ground state energy or minimal value of this expectation value. And we hope that this is the ground state or close to the ground state, although of course, many problems can arise. So as I said, this quantum circuit depends on parameters. It's sometimes called parameterized quantum circuit. And this part here is the classical optimization part. And that's why it's called hybrid quantum classical algorithms, because the expectation value, which is the costlier part to simulate with a classical computer, is the part that will be carried out by the quantum computer, and the optimization part, which we already know very well how to perform optimizations in classical computation, will be performed with our classical subroutine. So let me take a closer look on how these parts work. So we start with our objective function. As I said, it could be the expectation value of some Hamiltonian, or it could be something more sophisticated. But in the end, we will need to decompose it into Pauli strings, which are the operators that we can measure in our quantum computer. That means that even if we have so we start with a Hamiltonian with 2 to the power of n, where n is the number of parties or qubits that we have, big. So that's why exact diagonalization will scale very badly in classical simulations. But we move everything for a polynomial number of terms, which are the expectation value of these Pauli strings. So we are simplifying, and that's the advantage of using a quantum computer for that in the end. But as I said, this objective function could be other things, could be the fidelity with respect to a target state, which is something that will be used especially in quantum machine learning, in this variational quantum machine learning. Or it could be any combination of these expectation values. Then we have the parameterized quantum circuit. This is one of the open problems in this field, how we design this quantum circuit, because we have to find the trade-off between finding a good expressible ansatz, so something that we know for sure that we can prepare the ground state of our problem, and on the other side, something that doesn't require a huge amount of gates, because it will not be possible to be run in a real quantum computer. Because as I said before, we currently have quantum computers of a few qubits and with a lot of noise. So there are many strategies, and one of them are the problem-inspired ones. For instance, the unitary coupled cluster ansatz or the QAOA ansatz. They take the Hamiltonian, they take the problem, and they find a way to decompose it into quantum gates. So you know almost for sure that you will find the correct ground state. But the problem of these approaches is sometimes they require a lot of gates and a lot of circuit depth, so they are not feasible in current quantum computers. And that's why people came out with these hardware efficient ones, which the idea is we apply a layer of rotational gates, a layer of entangling gates, layer of rotational gates, and so on and so forth. So eventually we are increasing the expressibility of our ansatz, so we can move around this Hilbert space, and at the same time using gates that we know we can apply easily in our quantum computer. But on the other hand, it's not guaranteed that we will find the ground state. Maybe we need to find these particular layers structures, and that's not clear how to do that either. So that's an active field of research. And finally, the classical optimization part. This has also, so we need to compute the gradients of our circuit, of our parameters. And there are many ways to do that, but it's something that you should add to the computational cost of your algorithm, because these gradients can be mapped into expectation values. So you also need to compute these expectation values. So each time that you run your variational algorithm, you need to compute the expectation value of your operator plus the expectation value of all the gradients that you will use in the classical optimization subroutine. So that add a lot of measurements and a lot of things. And that's why these variational quantum algorithms, we need to be careful with how many parameters are we dealing with. And there are some strategies though to try to reduce the number of measurements, to reduce the number of gradients to be measured, etc. There are many of them. The one that I show here is just the most simple one, just to have some intuition, so we can compute this parameter shift rule easily, but this is not the most sophisticated one. And the scaling of this parameter shift rule is probably one of the worst ones that you can do in a real variational quantum algorithm. So let me finish this track with the example, one of the well-known examples, which is the variational quantum eigensolver. It was one of the first proposals of these variational quantum algorithms. And the initial goal was for chemistry, although you can extend the same idea to other fields. So in the original proposal of the variational quantum eigensolver, they wanted to compute the bond dissociation curve of this helium H molecule. So you start with the electronic structure Hamiltonian. And as I said, we have to decompose it into Pauli strings, because these are the expectation values that we can measure in our quantum computer. So we have a polynomial number of these Pauli strings. The more sophisticated is the electronic Hamiltonian, the more Pauli strings we will have. So it depends on how many degrees of freedom or how many orbitals do we want to introduce here. So once we have this Hamiltonian, we can generate the circuit ansatz using this problem-inspired idea, using the unitary coupled cluster ansatz. And the idea is the following. We start with the Hartree-Fock approximation, which is like the first order approximation, something that we know how to construct in our quantum circuit. And then we have the unitary operation, which is the cluster operator. And this cluster operator is also some terms of the Hamiltonian that are the excitation Hartree-Fock orbitals that we can map to Pauli strings using, for instance, Jordan-Wigner transformation. So once we have everything in Pauli strings, the exponential of some Pauli string it has a one-to-one map to a quantum gate. For instance, the exponential of of I to the Pauli string x is a rotational gate in the x axis. So we know how once we have this Hamiltonian decomposed into Pauli strings, we can directly compute and generate the ansatz that will prepare the ground state of our molecule. And the goal, as any other variational quantum algorithms, will be to minimize the parameters of these Hartree-Fock orbitals to obtain the minimum energy. This is related with the activation energy of our molecule, so we want to know what is the atomic separation at which the molecule has the lower energy. Some problem that happens in variational algorithms that is really important is the Var and Plateau. And as I said, in the variational quantum algorithms, we minimize the expectation values using this classical optimization subroutine. And we need to compute the gradients to do that in most of these approaches. If we don't have no prior knowledge of the variables in our parameterized quantum circuit, we initialize everything at random and try to find what is the optimal solution. The problem is we reach what is called Var and Plateaus, which is the expectation value of the gradients tend to 0, and also the variances tend to 0 exponentially with the number of qubits, which means that we cannot even apply second order terms in these algorithms, because the space of parameters is flat. We cannot see any minimum, we cannot see any maximum, we cannot move in any direction. So we don't have any clue where the minimum could be. So that's a problem, obviously, and it's related with because the Hilbert space is exponentially big, and you start at random, so you obtain what is called a 2 design. And in the end, what people is trying to figure out is strategies to avoid this Var and Plateau. For instance, some people came out with the idea of using local cost functions instead of global ones, or introduce some correlation between parameters. And in the end, the Var and Plateau can be solved or sorted if, first of all, if you have some problem-inspired answers that tell you where to start, or some initial good guess of the parameters. So you are close of this narrow edge, and you know that you can find a solution. But that's not possible in general. So that's why it's an active field of study how to avoid these Var and Plateaus. So let me check my time. Okay. So let me move to the third part, which is using these variational quantum algorithms, but for quantum machine learning, and because we will use some of these strategies later in the Meta-VQE. So first, I would like to stress out what is the difference, or what we understand as a difference between classical and quantum machine learning. So there are two things that we can discuss if they are classical or quantum. One is the algorithm. So is the algorithm run in a classical computer, or is the algorithm designed in a way that it has to be run in a quantum computer? And on the other side is what is the data? What is the origin of the data that we will manage? Is it quantum or is it classical data? So that's why what I will call quantum machine learning is anything that is run in a quantum computer eventually. So it could be data that is classical, for instance, some classification problem or image classification, whatever, but the data is classical. Or it could be a quantum. So for instance, there are some proposals that try to reconstruct the tomography or some density matrix from some quantum experiment using quantum machine learning. And of course, you also have machine learning applied to quantum, which is exactly the same idea, using quantum data, but you run everything in a classical subroutine. So let me also give you some intuition of how we move from classical to quantum neural networks in some of the approaches. They are not the only ones, of course, but I will just talk about the ones that are related eventually with variational quantum algorithms. As you may know, the classical neural network is composed of 3 steps, let's say. The first are the input neurons, and then we will have some hidden neurons in the middle that will process the data that is introduced from the input neurons. And until we reach the output neurons, which we construct the cost function, and we optimize the weights and biases of our hidden neurons with that cost function, trying to minimize this cost function. So similarly, in a quantum machine learning from a quantum machine learning point of view, we will have some part of our circuit that will encode the data, will introduce the data into the quantum state. Then we will have some processing layers, which will be also rotational gates, whatever, that will process this data, and eventually we will measure what is the state of these qubits, and depending on the value, we will reconstruct some cost function. And again, the idea will be to fine-tune the parameters of the encoding or processing layers in order to minimize this cost function. So the idea is very similar. So in that direction, I asked you a question. So what is the most simple but still universal model of neural networks? And the answer is a single hidden layer neural network. So it was proved in the 90s that if you have enough neurons, if only one layer of hidden neurons, you can approximate any continuous function with that. In general, this will not be practical, and that's why we also have deep neural networks, because we will require less number of neurons to do that. But if we can run everything in only one hidden layer, we can approximate technically any continuous function. So in that direction, what is the most simple but still universal quantum neural network framework? And the answer is a single qubit. With only one qubit, you can approximate any continuous function. Of course, this is not about quantum advantage, because a single qubit can be simulated in a classical computer. But the idea is, what is the minimal requirement, so we can start constructing from that. And the analogy goes in this way. As input the neurons process the data into the hidden layer and then to the output, in our single qubit quantum neural network, the processing, the input will be encoded into each of these individual elements, into these hidden neurons. So for us, the hidden neurons will be the parameters of our quantum gates. So what we call this strategy data reloading, because we have to introduce the data manually in each of these gates in a similar way that the input neurons introduce the data into each of the hidden neurons. So more intuition about it is with only one qubit. We will have at some point some layer after layer, which each layer will be a quantum gate. So a product of unitaries can be written as a single unitary. It's a matter of finding the Euler angles. It could be very complicated, but we can always find this unitary. So that means that if we start with some point and our correct level is in another part of our block sphere, we can go there in a very complicated manner using different unitaries, or we just find the correct unitary that goes there straight. The problem for quantum machine learning will be that if we have a different label, because our data has changed, if the unitary is exactly the same, we will reach the same point, obviously, so we will fail to find the correct solution. So what can we do to compensate that? And the answer is introducing some plasticity or something, that some parameter dependency in our quantum gates, so the operation becomes flexible and data dependent. And this is the idea of data reloading. So we will introduce the data along the circuit multiple times, so we are finding this parameter dependency. So the path this time will depend on the data, as it should be, because the label will be in a different part of our block sphere at some point. And this is some example of what is most general framework, which is the quantum feature maps. And as I said in the first slide in this part, we start with some encoding. We need to introduce the data inside of our circuit somehow. And this is called the quantum feature space. So we have some input space and move to the quantum Hilbert space. And then after that, we process this data. And we can also understand it as finding the correct measurement basis, so we can measure it in the correct direction. In a quantum computer, we normally measure in the Z direction. So that's why we need sometimes these processing layers, which are actually finding what is the correct basis that afterwards we can measure in the Z and find the correct state. So that's the idea of the quantum feature maps. Let me check my time. Okay. So the data reloading idea, as I mentioned before, is based in the universal approximation theorem. And I will just go very fast in this part. I can answer more questions about it later. But the idea is we will find a map, a one-to-one correspondence between applying different hidden neurons and constructing this kind of function that at some point will be able to reproduce any continuous function. And this is based on the fact that a single qubit gate is an SU2 operator. So if and where the sigmas are the generators, and we use this linear encoding in particular, which is the same kind of encoding that we use in neural networks. And these rotational gates will play the role of the activation function in our quantum neural network. So if we multiply multiple products of SU2 operators, it will be eventually another SU2 operator, but only in a very complicated way, or all the Euler angles will have some dependency. But in the end, whatever dependency they have, it will be some continuous unbounded function, because it's a combination of trigonometric functions, cosinus, sinus, etc. So that's the point that we needed to prove this continuous approximation. So in the end, we can just find a way to put everything together. So eventually we will have this sum of terms that will have this one-to-one correspondence with the universal approximation theorem. And of course, there's just some intuition. If you want to see a more rigorous proof, I recommend you to check these two references, where they also explain how a single qubit can be used, and also multiple qubits can be used to obtain all the Fourier coefficients. So we can approximate any Fourier series with quantum circuits. And this applies to one qubit, but the idea behind it, we believe, and we were benchmarking that in our previous work, that it will work in a similar way with two qubits, although we didn't prove this universal approximation theorem. But then afterwards, they came these references that show that these quantum circuits can approximate Fourier series. So it seems that it will work in more than two qubits. So with that, I have all the ingredients needed to design this meta-variational quantum eigensolver. And let me go back and remind you what is the true goal of a variational quantum eigensolver. So I didn't explain the full story. So as I said, the variational quantum eigensolver aims to find the ground state energy of some Hamiltonian. But the true goal of a variational quantum eigensolver is not only to obtain the ground state energy, is to find where this ground state energy is. So we want to see what is the atomic separation in this particular example that has the lower energy, the lower ground state energy. So in the end, we need to run a scan. We need to compute a variational quantum eigensolver in different points for different atomic separations. So basically, the Hamiltonian is apparently the same, but we need to change the parameter and run an individual VQE. That means the optimization, all these parts, until we find this curve and we see, okay, this is the minimum, this is where the minimum is located. So each of these blue points are individual VQEs with all the computational costs that means. So the question that we had is, can we try to avoid having to compute all these individual VQEs? So for instance, only finding this interesting energy region and maybe running them so there are some more sophisticated minimizations, but trying to avoid to compute, for instance, the atomic separation at 300 picometers, because we are not interested in this region. So why we should compute all these VQEs? And as some intuition of how we will do that is there are some ways to simulate analytical models in a quantum computer. By just finding the same steps that we will use for exact diagonalization, we can map them into a quantum operations. So this is the example of the Ising model. It can be solved analytically. And we can just find the gates that perform the Jordan-Wigner, the Fourier transform, and the Bogoliubov transformation, and map them into a quantum circuit. And with that, we can compute everything about this model in particular. So if we do that, you can see that the parameter of the Ising model, so the transverse field and the coupling constant, they are introduced in the rotational gates in the Bogoliubov transformation. But the rest of the circuit is completely, it doesn't care about the parameters of the model. So in a way, we are encoding the parameters of our Ising model into this first layer of gates, which is the Bogoliubov transformation. And afterwards, we process this state and find the ground state and also other states in this particular example. So taking that in mind, we will think about how can we do this with general Hamiltonians? If the general Hamiltonian cannot be solved analytically, that will not be as easy as just following a receipt, but we can use these ideas of data reloading and quantum machine learning to find what is the best way to encode this data. Maybe we don't know how we should encode this data, as is this case with the ASIC model, but we can try to variationally find what is the proper encoding. And this is the idea of the Meta-VQE. So instead of having to run an individual minimizations to obtain the energy profile and eventually find what is the minimum energy, with Meta-VQE, we will take some training points. We will find the minimization of all these training points in an individual objective function. And once we have that, we can run more VQEs, but this time without the optimization part. So we obtain this energy profile without further optimizations. So once we have this profile, we can identify what are the interesting regions, and maybe afterwards, if it's necessary, run more sophisticated minimizations, but only in this particular region and not in all of them. So in the end, we are trying to fit the function by trying to find what is the proper encoding of all these parameterized Hamiltonian, parameters from our Hamiltonian. How we will do that by defining, as before in quantum machine learning, variational quantum machine learning algorithms, by defining the encoding gates and then the processing layers. So the encoding will include the training points for this parameterized Hamiltonian, and then also some set of variables that we will need to optimize. And then the processing units will only contain variables to be optimized, and we measure the expectation value of the Hamiltonian. And we repeat the process multiple times until we are done with all the training points. And once we have all these expectation values, we put all of them together and we minimize all of them at the same time for the same variables. So these theta and phi variables are the same for each training point. The only thing that changes from one circuit to the other is the parameter of our Hamiltonian. So the output of all of it will be some optimized thetas and phi parameters of our quantum circuit. Once we have these parameters, we have two options. The first is the pure Meta-VQE option, which is running the circuit with the test points this time, but with the optimized parameters. So we only run the circuit, compute the expectation value, and that's it. We don't have any classical loop to optimize anything further. So that's that we run these simulations, and I will show you later some results. And we find that we see the profile of the energy, but it's not as precise as you should expect with an individual minimization of a VQE. So that's why we also have the option 2, which is individual VQE as the standard one, but instead of starting at random, we start from the solution of the Meta-VQE. That means that the optimization is much farther because we are close to the solution already. So we are avoiding these Var and Plateau problems. And also we obtain a good accuracy because it's less likely that we will end up trapped in local minima. We run the test of Meta-VQE with some spin Hamiltonian, in this case, the XXZ spin chain with this delta anisotropy parameter. And we use this because it's a circuit that is really difficult. So it can be solved analytically with the beta ansatz, but this beta ansatz is not clear how to map it to a quantum computer. So it was a good test. And at the same time, it has multiple phase transition. It has 2 phase transitions. So the ground state will change. That's also like a good worst case scenario model because many things can be wrong in this model. So we wanted to benchmark how good a Meta-VQE could be in this bad environment in this case. And this is the results. So for a 14-qubit simulation, and we use the linear encoding in this case. So in each layer of rotational gates, we introduce the parameter of our Hamiltonian in a linear function where these W's and P's will be parameters to be optimized. And then layers of alternating synods. This is called a hardware efficient ansatz. So it's very easy to define these ansatz. And the result shows that the Meta-VQE can see what is the energy profile, but still it lays away from the exact solution. But then when we we check the absolute error when we run this optimized Meta-VQE versus the standard VQE, the optimized Meta-VQE is more consistent. So it's less likely that we have jumps because we just get trapped in local minima. And it also reaches lower energies, probably because we are closer to the solution. So again, we are not getting trapped in local minima as easily. Still, we are not finding the proper wave function for greater deltas, and this because this is a highly entangled state, and we started from a product state. So the ground state energy changes drastically. So of course, it's something that we can assume is that the encoding probably will not be the same in one phase than in another phase. So we should be careful each time that we run this kind of algorithms in models that are critical, because the ground state will change drastically, and probably the encoding is not cannot be used in different phases, the same encoding. Then we tested with a molecule, with the H4 molecule with 8 spin orbitals in this TO3G basis set. And this time we use, instead of a hardware efficient ansatz, we use the unitary coupled cluster ansatz for k = 2 in this case. It's a kind of, you can think about it like a kind of Trotter decomposition of the Hamiltonian, where we use 2 layers of that. And in this case, we wanted to test not only linear encoding in the rotational gates, but also nonlinear encoding with these floating Gaussians. So we are adding more parameters, but we use these floating Gaussians because we know the ground state of these molecules resembles this kind of behavior. So we were trying to use everything that we know about our problem to help our Meta-VQE. And we find that the Meta-VQE is better than the standard VQE when the initial state is the 0 state. Is not better when the initial state is the Hartree-Fock state, which is the first order approximation. But then when nonlinear encoding, it's much, much better than the VQE encoding, than the standard VQE. So here we see there is a clear advantage of using Meta-VQE, because we are not only saving steps in our computation, because we don't have to run for all for all points of our Hamiltonian spectra, but also we find much better accuracy in energy. So it's a double advantage in this case. And finally, we also tried with a single transmon. So this is a simulation to simulate, so how a quantum computer will simulate another quantum computer. So the transmons are the superconducting qubits. And this is so there are some models that that know how to map this transmon physics into a quantum circuit, and we can simulate that. And we use that as an example of other kinds of circuit ansatz, which instead of control knot gates, we have these XX gates, which are other kind of entangling gates. And again, the VQE, it's the Meta-VQE, the optimized Meta-VQE is much better than VQE. And we also tested against a VQE that we call SMART, which means that we are using some optimization strategies, like using the previous optimization point solution to start the next one. So we are helping our VQE. But still, the optimized Meta-VQE finds a solution with better accuracy and also much faster. It converges much faster. So let me just close my talk with some conclusions about Meta-VQE. The first is that it can be used to scan over these Hamiltonian parameters to identify these interesting energy regions, so we avoid to compute all these uninteresting points that will only add computational cost to our algorithm. So we are reducing this computational cost. And then we can use the parameter solution to run a more sophisticated optimization, and we call that optimized Meta-VQE. And we proved that this is much faster in conversions, and it also avoids getting trapped in local minima. So potentially, although we didn't analyze that in detail, but potentially avoiding these Var and Plateaus, because we are not starting at random anymore. We are starting in a region close to the solution. And then the encoding strategy probably help this to avoid these Var and Plateaus, because there are some works that prove that if there is some correlation between the parameters of the circuit, you can avoid these Var and Plateaus. And in our case, these correlations are the parameters of our Hamiltonian that appears in multiple parts of the circuit in different quantum gates. So if you are more curious about this Meta-VQE, I suggest you can check the code and demo that is published in our group repository, which uses Tekila. So it's could also be used as an example of how to use Tekila for constructing a more sophisticated algorithms. And with that, I would like to thank my collaborators and also all Tekila developers and people that were involved in this noise intermediate scale quantum review. Thank you very much.
Great, thank you so much, Alba. That was a really interesting talk. So now we can move into the Q&A. And I see that we already have a question. So Harm Pell says, were these simulations done on an actual noisy quantum device? If so, how did the noise impact the result in comparison to the VQE?
No, these simulations were complete wave function simulations, so it's not even sampling. So we use QLAX, which is one of the backends supported by Tequila, which simulates the wave function. So it's a classical simulation of what will happen in a quantum computer without noise. We then introduce noise. If you introduce noise, of course, the results will be much worse because you have noise. Also, the problem with noise is it also can lead to Var and Plateaus. So Var and Plateaus appear from many fronts, and one of them is also noise. If your device is too noisy, you will have, no matter what you try, even if you start in a good point in your Hilbert space, it doesn't matter. You will reach Var and Plateaus. The same if you have too much entanglement, curiously. So of course, with a noisy simulation, I will expect the result will be worse, of course, and also maybe the Var and Plateaus will appear very quickly, so we cannot deal with them. But that's what happens in general each time that you run anything with noise. But at the same time, you can also try to mix it with one of the error mitigation techniques. So there are a set of classical post-processing techniques that are called error mitigation, that helps you to estimate what will be the result of your computation if you didn't have noise. So you run your circuit in a different ways, and you can kind of extrapolate what will be the result without noise. And this is also a technique used. So something interesting that you can check is running this kind of Meta-VQE with noise and see with error mitigation if you can recover a similar result as a noiseless simulation. That could be something that could happen. But yeah, as I said, noise will also introduce other sorts of Var and Plateaus. So
great. Are there any other questions? Okay, I suppose while we wait.
Yeah, I see one question. Sorry.
Oh, do you see? Oh, here we go. So my my internet connection cut out halfway through, so I think I might have missed one of the questions. But I can see one here now saying, so Kasim Habib says, it was an interesting talk. Can you please arrange another talk? Oh, sorry, that's not a question. But okay, he says it was an interesting talk.
That's for the organizers, maybe.
And yes, I suppose I have a question about. I know in the usual VQE, you can encode symmetries in the ansatz, which sort of has some kind of computational advantage. Can you do the same here, or is it more difficult to do?
Sorry, could you repeat the question?
So in the normal like ansatz preparation, I think you can have like an ansatz which preserves like, say, particle number or something like that. Which makes it easier to find. Can you do something like that here? Or?
Yeah, there are some ansatz. So yeah, I mean, it's a huge field in this direction, which are trying to see, I don't know if that's what you mean, for instance, checking with some extra qubits, you check if the parity is conserved or of these kind of things. So you know if your solution is going in the right direction or not. Because if at some point, so you expect the number of qubits of states or qubits or parity, whatever. So you have a way to quantify what's going on in your ground state, the one that you are computing with your quantum computer. If you can track that, then you can discard those solutions that are not parity conserving, for instance. So you are introducing some symmetries in your ansatz. In a similar way, you can also know if you have translational invariance in your model. You will expect that your quantum circuit ansatz will be kind of symmetric somehow and should respect this translational invariance. So it doesn't have any sense that you put some ansatz that is not symmetric or these kind of things. So you can try to do these strategies if you have more knowledge about your Hamiltonian or about your model, of course. And these are kind of the problem-inspired ones. So that's the goal. For instance, the QAOA, you can understand it as a kind of Trotter decomposition of a diabatic evolution somehow. So you take your Hamiltonian and you apply Trotter decomposition, and you take different layers of this Trotter and map them to a quantum circuit. The more layers you have, the more precise will be your solution. But it's also going in that direction. We are taking something that we know and we are decomposing it and trying to find the mapping to the quantum circuit.
Okay, thank you. So Arnaf LV says, can you elaborate on the idea of Pauli string expansion of the Hamiltonian? Is it like writing the Hamiltonian using the Pauli matrices?
Yeah, exactly. So you can, so you have some matrix, which will be your Hamiltonian. So imagine with only one qubit, it's a 2 times 2 matrix. And any general 2 times 2 matrix can be decomposed into different, into some coefficient times sigma x, some coefficient times sigma y, some coefficient sigma z. And you have to, you need to find the coefficients. And similarly, for more than 2 qubits, you can decompose it into 1 or the Kronecker product of 2, the Kronecker product of 3, and so on and so forth. So it's a matter, there are some algorithms that find this expansion. So you are decomposing your Hamiltonian matrix into Pauli terms, or so Pauli matrix terms. So when you have to compute the expectation value, you only compute the expectation value of your Pauli strings. That's why they are called Pauli strings, because it's not only one Pauli matrix. Sometimes it's Pauli matrix, Kronecker, another Pauli matrix, Kronecker, and so on and so forth. And then after that, after you have this expectation value, you sum all of them together with the corresponding parameter in front of them.
Great. Okay. So we have no more questions. So I suppose we can end it there. So thanks again to Alba for giving some insight into the current quantum algorithms and the issues we're trying to overcome. So next week, we're just going to have a single speaker, and that will be on Thursday. And that's Professor Jean Bricmont, who's going to be speaking on the Broglie-Bohm theory as a rational completion of quantum mechanics. Yeah, so keep an eye on the Facebook page for that. And finally, if you haven't already, please make sure to subscribe to the mailing list, which can be done on the website. Okay, so thanks again to our speaker, and
thank you very much.
Goodbye.
Goodbye. Have a nice day.
You too.